Sorry about the phone call there. It was the Academy Awards honoring me with the Grammy for best math videos ever. Just kidding. How many zeros does this function have? So you're going to look at the power, the highest power. Now be careful, this is not the highest power because this thing is not in standard form, which is kind of tricky. So the highest power is 5, which means there are 5 zeros the function could have. What is a polynomial function of least degree? So that means the smallest power possible. It has real coefficients, a leading coefficient of 1, and then the zeros are x minus 2, the zeros are minus 2, positive 3, and positive 4. And I think this is the most important place to start. When you have these zeros, it means that you have these factors. The factor that gives negative 2 a 0 is x plus 2. Because if I plug negative 2 in for here, it makes this equal 0. A positive 3 gives you a factor of x minus 3, and a positive 4 gives you a factor of x minus 4. So from the zeros, we're able to get into factored form, and then from factored form, with some work, we'll be able to get it into standard form. So that way we know what degree it is. So we're trying to get it into a traditional standard form looking polynomial. I just think it works out better when I have 3 binomials that I'm multiplying together. I actually like to take the last 2 and multiply them together. You get x squared minus 3x minus 4x. I think you might get those switched in a different order if you do it the traditional way. But you get that, which equals x squared minus 7x plus 12. However, folks, this all right here is going to get multiplied by the x plus 2. And on our test, a lot of us at this point distributed this x and this positive 2 to all 4 things over here. I think if you take a second to combine like terms, it helps because there's just a lot less math that you have to do from there. A ton. So I combined negative 3x and negative 4x and got negative 7x, and now I distribute the x only to 3 things. 1, 2, 3, and I'll distribute the 2 to these 3 terms. So instead of getting 8 terms here, I'm going to get 6 terms, which is nice. It's worth the little combining that I did. So I get x to the third minus 7x squared plus 12x because I distributed an x to each of these, so it added a power to the x's, or it added an x to the 12. Now multiply everything by 2. So I get 2x squared, not modifying or changing the powers at all, minus 14x plus 24. Now we're super close. We just need to combine like terms. I don't have an x to the third anywhere else, so I bring that down. X squared, so I get negative 5x squared. X and x, I get negative 2x. And then at the end here, I have a constant, which is 24, positive 24. Oh yeah, that looks good. So we got the zeros, took the zeros, put it in factored form. We multiply our factored form together to get our standard form. What are all the possible rational zeros in this expression? So we're going to take the factors of our last term, our constant, and divide it by all of the factors of our leading coefficient. So factors of 12 divided by factors of 3. So factors of 12, 1, 2, 3, 4, 6, 12. Factors of 3, 1, 2, 3. Now the deal is you need to take this 1 on top and divide it, well, actually I'm going to take all of these and divide them by 1, which doesn't really do anything, right? By the way, this is always a positive and negative. So it could be positive or negative 1, positive or negative 2, positive or negative 3, 4, 6, and 12. Then take the numbers on top, the numerators, and divide them by 2 instead. So take all of these, divide them by 2. So that's going to give you 1/2. 2 divided by 2 is 1. I already have it. It's going to give you 3/2, which I don't have. 4 divided by 2 is 2, which I already have. 6 divided by 2 is 3, which I already have. And 12 divided by 2 is 6, which I already have. And then, last but not least, take those numbers on top and divide them by 3. 1 divided by 3 is 1/3. 2 divided by 3 is 2/3. 3 divided by 3 is 1. Got it. 4 divided by 3 is 4/3. 6 divided by 3 is 2, which we already have. 12 divided by 3 is 4, which we already have. I wish I could sneak that number on the end of this. So it's plus or minus all these values. Those are the potential numbers that I could plug into X to get a 0 out. It's a long list. Thankfully, we only have to list the list and not actually check them. Number 6, find all the zeros for this function. So now we're actually going to have to do what we just did up here. Try to experiment to figure out what a 0 could be. Well, it could be 1 or 7, because 1 times 7 equals 7. So that's a factor of my constants. I should write that down. Constant, which is 7, factors. Well, that's 1 and 7. And then my leading coefficient is 1. So the factors of 1 is 1 and 1, which is awesome. So I get my new list now for this is positive or negative 1 and 7. So to be clear, there are my list really is positive 1, negative 1, positive 7, negative 7. There are 4 numbers that I need to check here. Now I'm hoping I'll get a 0 right away. So I'm going to check positive 1. You can choose any of these 4 numbers to see if it spits out a 0. So I'm checking 1. Coefficients, list those out in your synthetic division. So we get 1, 9, 15, and 7. Drop down a 1, multiply, add, multiply, add, multiply, add. Bummer, dude. Didn't get a 0. So positive 1 is not a 0 of this polynomial. I didn't find it yet. Let's try negative 1. So really we're just copying those coefficients again because we're still working with the same polynomial. Drop it down, multiply, add, multiply, add, multiply, add. Woo-hoo-hoo-hoo. Remainder of 0, or in other words, when I plug negative 1 into this function, it gives me a 0, which means 7 is the constant of the remaining polynomial. 8x is the next term, and 1x squared. So the directions say to find all of the zeros. I've just found 1, but now look at this. I have 1x squared plus 8x plus 7, and I want to know what makes it equal 0. Check if it's factorable, and it is. Otherwise, we could use like the quadratic formula. We could graph it. So numbers that multiply to 7 and add to 8. This one kind of freaks some people up because the multiplier number is smaller than the adding number. And it might mean that 1 is one of your numbers. So 1 and 7 makes it happen. So I can rewrite this. So this is in standard form right now. I can rewrite it in factored form. I've just started the factoring process. So I can rewrite this as x plus 1 times x, parentheses, x plus 7 equals 0. Now that it's in factored form, folks, remember the zero product property tells us that anything times 0 is 0. So if I could make this whole thing, this parentheses, become a 0, that'd be great. What makes it happen? If x is negative 1. That makes this 0, 0 times anything is 0. I can get my other solution by figuring out what makes this equal 0, and it's negative 7. So my solutions are negative 1. I got that by using synthetic substitution. And by the way, you could just check the other numbers and get the zeros that way. It's multiple choice as long as I see work. I don't care how you do it. I got negative 1 again, so it's called a double root. And then I got negative 7 for another unique 0. There we are for number 6. Number 7, describe the end behavior. So the important things to know, and this is stuff that you should go to your notes to practice first to see if you can find it. If your power is even and you have a positive out in front, it's going to be a positive happy face parabola, like when we have x squareds. If you have, but it doesn't have to be x squared, it could be x to the 6th because that's also an even. When you have an even power with a negative coefficient in front, it's going to make it a frowny face. So the endings are the same here. They're both going up to infinity, positive infinity and positive infinity. Here, they're both going down to negative infinity and negative infinity. Forever and ever, they're going down that way. Whoa, that was a bad line. If you have an odd power, but it's positive, think of it as being a positive slope. If m, or the slope, is positive, it's going to look like this. So now it's not going to be a straight line though, because if the power is more than 1, it's going to make, you're going to get some curves in it. It's going to go like that. All right, last example. What if the slope is negative? Well, a negative slope of a linear equation is down like that. So what if we have a negative x to some odd power greater than 1? Well, then it's going to go down and to the right, but it's going to curve as it does it. Slither down and to the right. There we are. So which one is it here? We have an even power, so we're looking at red, and it's negative. So the end behavior now is, how we write this out, maybe get rid of all of this stuff. Oh, Bessie. Let's just look at our, just a second. I'm going to make it happen. I'm going to commit to this. I'm committing. Oh, no. My computer's been acting funny too. Everything's, oh, just a second. Should just drag down. Whatever. I'm going to highlight. I think I'm going to highlight. Holy God. No, this is bad. Okay. Positive thoughts. Positive thoughts. So we realize that it's this situation right here. So how do you write this? It'll be a fill in the blank. It'll say something like this. As x goes to negative infinity, f of x goes where? Well, so when they're talking about when x goes to negative infinity, here's your x-axis. This is positive infinity for x's. This is negative infinity for x's. Negative infinity for x's. So what they mean is when it's going to the left, what is y doing? When as x goes to the left, as the graph goes to the left, what is y doing? Well, y is going down to negative infinity forever and ever. And then the second question they'll ask is, all right, well, so as x goes to positive infinity, which means as x goes to the right, or the graph goes to the right, what's happening to f of x, which means y, which is the height. As we go to the right on this graph, we are going down, which eventually goes to like negative infinity. So there's our end results. You plug in negative infinity for both. Here, as x goes to negative and positive infinity, they both go to positive infinity for the y's. And here it would be one of each. Here, as x goes to positive infinity, so does y. Here, as x goes to negative infinity, y also goes to negative infinity. Here, it's opposite. Here, as x goes to negative infinity, y is going to positive. That'd be the fill in the blank there. And as x goes to positive infinity, y is going to negative infinity. All right, that was fun. Woo, chapter 7.